it's possible to implicitly control a system by spoofing inertial sensors. Means inertial sensors can be used in various applications when motion feedback is needed. There are two types of inertial sensors. Accelerometers measure linear accelerations. And gyroscopes measure angular velocities. They use a mechanical structure similar to a mass spring system to sense inertial stimuli and generate electrical signals to depict it. While the size and the weight of main sensors are significantly reduced, the miniaturized sensing structure could suffer from resonant acoustic interferences. In security-related researches, Rocking Jones' paper shows that a drone could be caused to lose balance and crash by disrupting the gyroscope with resonant sound noise. Furthermore, the Walnut paper showed it is possible to control the output of exposed accelerometers connected to Arduino by acoustic attacks. However, they took a white box approach, and we find it is difficult to implement their methods in a black box approach, especially when there are sample rate drifts. In their white box settings, the drifts could limit their control to 1 to 2 seconds. In a white box approach, the sensor is connected to Arduino. Attackers could monitor the real-time sensor output while tuning acoustic signals. Experimental settings, such as sample rate of the sensor, could be accessed and customized by attackers. However, when attacking sensors embedded in real devices, the attacker usually could not access the microprocessor board in the system and cannot access the real-time sensor data as well as the sample rate. So, to investigate if we can control real systems by acoustic attacks, we took a black box approach. In a black box approach, the attacker cannot access or modify the sampling process as well as the sensor data. Only actuation decisions made by the system could be observed in the real world. Another problem is the sample rate drift. In a black box approach, sample rate drifts make the system unpredictable and could cause troubles to attackers. The main problem in our work is how to non-invasively control the output of embedded inertial sensors despite the sample rate drifts. In another word, we took a black box approach. First, we found the sample rate drifts amplification theorem. We proposed two new methods to control an oscillating digital signal when there is undersampling. We devised non-invasive attacks on embedded inertial sensors. We evaluated our attacks on 25 devices and demonstrated implicit control over different kinds of systems. Furthermore, we proposed the automatic attack when sensor feedback is available. We are the first to develop a program to modulate acoustic signals automatically in such attacks. Finally, different from attacks using resonant sound, we found it's also possible to spoof the sensor with non-resonant frequencies. First, let's look at acoustic injection. Sound waves at frequencies close to the natural frequency of the sensing structure cause resonance and induce analog signals. Since the frequency of injected acoustic signals is usually much higher than the sample rate, it will be undersampled. The analog signal with a frequency f would be aliased to a digital signal with a frequency epsilon. When f is an integer multiple of the sample rate, the digital signal will be a DC signal. In the prior work, they need to induce and maintain the DC signal to control the sensor output. However, we found it is hard to maintain a DC signal on real devices. After investigation, we found sample rate drifts play an important role. This is the output of a gyroscope in iPhone 5s when we inject acoustic signals with a fixed frequency f. While f remains the same, we can observe that the frequency of the output epsilon keeps changing all the time. So from equation 3, we know this is caused by a drifting sample rate. For instance, when f is 20 kHz and the sample rate is 200, without the drift, the digital signal is a DC signal. With 1000 drift, the frequency of the digital signal would be 0.1. With 100 drift, epsilon would be 1 Hz. In this case, the sample rate drift is amplified 100 times in the frequency of the digital signal. Due to the amplification effects, it is difficult to induce and maintain a DC signal as in prior work. As a result, the induced output will be oscillating, and we need to find new methods to control it. From the picture, we can see when a signal is sampled correctly, the adjacent digital amplitudes AI and AI plus 1 are correlated. However, when the signal is undersampled, AI and AI plus 1 can be independent. This allows us to adjust different digital amplitudes to modify the shape of the signal. With this capability, we proposed the side swing attack. Many systems compute the accumulative hanging angle and make actuation decisions accordingly. However, in denial of service attacks, the hanging angle fluctuates and cannot be controlled. In side swing attacks, in one cycle of the digital signal, when the induced output is in the target direction, we increase the amplitude. Otherwise, we decrease it. In this way, the hanging angle can be accumulated in the target direction. Our third theoretical contribution is phase pacing. We found that by switching the frequency of the analog signal, we could induce a phase change in the digital signal. We can see in the picture, without phase pacing, the digital signal oscillates. With phase pacing, that means we switch the frequency of the analog signal from f1 to f2 at time tc. The moving direction of the digital signal is inverted. This is caused by a phase change induced in the digital signal. To induce a phase change, f1 and f2 need to satisfy the condition of phase pacing. Based on our phase pacing model, we devised the switching attack. The basic idea is to manipulate the sensor output by repetitive phase pacing. As we can see, by switching the frequency of the analog signal between f1 and f2 alternatively, the attacker could induce a phase change to invert the moving direction of the signal again and again. The cumulative hanging angle keeps increasing in the target direction. This picture shows the times when attackers need to change the amplitude of acoustic signals during side swing attacks. This one shows the times when attackers need to switch the frequency of acoustic signals during switching attacks. However, in our black box approach, since attackers could not access the sensor data, it could be difficult to decide when to tune the signals. We found it is possible to estimate the induced sensor output by observing the target system. We can see from the picture, by observing consequent actuations of the system, attackers could estimate the status of the induced sensor output. In this way, they could know when to tune acoustic signals. We measured the sound pressure level of speakers we used. For each attack, we selected a speaker that has a maximum sound level based on the attack frequency. Generally, for frequency lower than 21 kHz, the sound level is between 120 and 130 decibels. For frequencies higher than 121 kHz, the sound level is between 110 and 120 decibels. The speaker is powered by a 50-volt audio amplifier, and the signal is generated by a function generator. We also attached a directivity horn to the speaker to focus the sound waves and improve the attack distance. We tested 10 closed-loop control systems and found 6 of them could be implicitly controlled by attacking the gyroscope with inaudible sound waves. It is also possible to attack accelerometers, but it is audible and tends to make the device lose control. We measured the maximum horizontal distance that a target device can be affected by our sound source. However, in practice, to achieve adversarial control, the attacker needs to get closer. We tested 4 types of closed-loop control systems. It is possible to manipulate the moving direction and speed of motors in transporters or robots. It's also possible to manipulate the orientation of stabilizers. This is a demo of switching attacks on a self-balancing transporter. We used ultrasonic signals to attack the gyroscope. By switching the sound frequency back and forth, we make the motor rotate to the target direction. We summarize our attack results on 15 closed-loop control systems in Table 2. We found 11 of them are susceptible to implicit control. In remaining devices, 2 devices can be controlled very limitedly due to insufficient sound strength. We tested 5 types of open-loop control systems. Our attacks could manipulate the cursor of a 3D mouse or the orientation information of VR devices and smartphones. This is a demo of side swing attacks on a gyroscopic screwdriver. We tighten the bolt on a screw and take it out by attacking the gyroscope. It is possible to control the direction and the speed of the motor. In the videos, I was very busy turning the buttons to tune the signal. So I'm wondering, is it possible to use a program to do the work? We found that in certain situations, it is possible to gather real-time sensor data. Smartphones provide such APIs with no permission required. Autonomous agents like drones often transmit unencrypted inertial sensor data. So we input the inertial sensor data stream of a smartphone to a program we made and used the program to modulate acoustic signals automatically based on the sensor data. Our program can actively adapt to the sample rate drifts. The right picture illustrates how the program calculates and adapts to the drifts. The basic idea is to keep the integer multiple of a drifting sample rate in the midpoint of F1 and F2. We implement our automatic switching attacks in different platforms. In this demo, the JavaScript program used the built-in speaker to play resonant sound and induce the positive output in the x-axis of the gyroscope. So while the phone is stationary, the gyroscope data would show the device is rotating in the positive direction of x-axis. The sample rate of the web application is only below 20 Hz, and we slightly move the phone during the experiment. We also implemented the attacks in an Android app program to manipulate the orientation of Google Maps, and an iOS program to manipulate a user's view in VR applications. Up to now, all attacks on inertial sensors exploit resonant sound. We found it is possible to spoof the sensor with non-resonant frequencies. We put a Google Pixel smartphone on a vibration platform. We implement side swing and switching attacks with vibration signals around 20 Hz. While the phone remains on the platform, the accelerometer data shows it is launched to the sky with and has accumulated a speed of over 70 meters per second. So possible countermeasures include damping and isolation. For example, microfibrous clothes or microisolators might be used to damp sound and vibrations without causing too much size overhead. For systems with vibration sources, such as speakers, it would be a better design to keep them away from inertial sensors. Other approaches include filtering and sampling. For example, if a low-pass filter is configured correctly, out-of-band analog signals would be eliminated. Special sampling techniques, such as randomized sampling, could be used to mitigate attackers' ability. A dynamic sample rate might be used to make the frequency of the induced digital signal unpredictable to attackers. Finally, it might also be possible to use redundancy-based approaches to enhance the resilience of the system under attack. It could be more difficult to attack moving targets, such as a drone. In this experiment, we try to make a drone tilt to the left twice and tilt to the right twice. However, the attack effect is not so obvious, and sometimes it did not tilt to the direction as we expected. Another problem is a sound source. The effective range of our sound source is still very limited. It might be possible for an attacker to buy or build a more powerful sound source. Theoretically, with 8 coherent sound sources, the possible sound level increase could be 18 decibels. So in this work, we took a black box approach and devised non-invasive attacks against embedded inertial sensors to deceive the system. Our attack evaluations on 25 devices showed it is possible to implicitly control different kinds of systems by acoustic attacks, injections on inertial sensors. Our work showed that if attackers could spoof the output of embedded sensors in a control loop, they could trigger and manipulate actuation decisions made by the system without modifying the system directly. Here are the references. Thank you for listening. Now I'm happy to take questions.